Hello everyone. I'll be explaining the flood fill algorithm, one of the most fundamental algorithms used in polygon filling techniques in computer graphics. So, let's get started. In this presentation, we aim to achieve 5 key objectives. First, we'll understand the concept and working of the flood fill algorithm. Second, we'll differentiate between 4 connected and 8 connected flood fill methods. Next, we'll look at how this algorithm is implemented both recursively and iteratively. We'll also identify common issues like stack overflow and explore how to avoid them. And finally, we'll explore real-world applications where flood fill plays a major role. Here's a quick look at what we'll be covering today. We'll begin with an introduction to polygon fill algorithms. Then, we'll dive into the flood fill algorithm, learn about its types, working mechanism, and two main approaches, recursive and iterative. We'll also go through the pseudocode, a numerical example, real-life applications, and finally, wrap up with a summary. Polygon filling is essential in computer graphics. It helps in coloring enclosed areas, making it useful in games, image editors, and CAD tools. These filling algorithms play a crucial role in converting vector-based graphics into raster format, which is what we see on the screen. They also improve user experience by enabling quick and smooth area coloring, such as with the paint bucket tool in digital tools. The flood fill algorithm works just like pouring paint into a closed shape. The paint spreads in all directions until it hits a boundary. It fills connected pixels that share the same color, starting from a seed point. This spreading can be done either using recursion or with a queue. One of the great things is that you don't need to know the shape or size of the region beforehand. It processes each pixel by checking if it meets the conditions, then continues the fill from there. There are two types of connectivity in flood fill. The four connected fill considers only the top, bottom, left, and right neighbors. The 8 connected fill, on the other hand, also includes diagonal pixels, providing more thorough coverage. Here you can visually compare the two. In 4 connected fill, only horizontal and vertical pixels are checked. In 8 connected fill, diagonal pixels are also included, making it more complete, especially for diagonal shapes. Let's understand how the algorithm works. First, it begins at the seed pixel. If the pixel matches the target color, it gets filled. Then, it checks its neighboring pixels. It keeps repeating this process until there are no more connected pixels left to fill. During this, it also ensures the pixel is within image bounds and hasn't already been filled. It's important to understand the difference between flood fill and boundary fill. Flood fill works by replacing a target color, while boundary fill continues until it hits a specified boundary color. Flood fill is more common in applications like MS Paint, whereas boundary fill is used more for drawing shapes with outlines. The recursive method is quite straightforward. It checks all four neighboring directions, top, bottom, left, and right, but there's a catch. It can lead to stack overflow if the fill area is very large due to too many recursive calls. This method is similar to the four connected approach, but with 4 additional directions, diagonal neighbors. This gives better coverage, especially in slanted or curved shapes. But again, be cautious of stack overflow issues. To solve the stack overflow issue, we can use the iterative method. This version uses a queue to store the pixels that need to be filled. It dequeues one pixel at a time, fills it if needed, and adds its neighbors to the queue. This method is memory efficient and handles large fill areas better. Here's a simple matrix to show how flood fill works. Initially, we have this 3 by 3 grid with ones and zeros. We apply the flood fill starting from the top left corner, 0, 0, and change all connected ones to 9s. You can see how the algorithm fills the top left region while leaving zeros and unconnected ones untouched. Flood fill is used in many real-world applications. It powers paint tools like the fill bucket in MS Paint, helps mark territories in games, supports pattern recognition and image segmentation. It's used in CAD software, medical imaging for identifying regions, flood simulation models, maze solvers, and even OCR systems for text extraction. Some key advantages of floodfill: it's easy to implement, supports both recursive and iterative styles, works well on irregular and non-convex shapes, can be used in both 2D and 3D grids, and it can be optimized and combined with other algorithms like scanline fill. However, it does come with some limitations. Recursive methods can cause stack overflow. It can be slow for high resolution images. It may accidentally overfill areas if not coded carefully, and memory usage increases for complex shapes or large images. To overcome these limitations, we can apply some optimizations, use the iterative version to avoid memory issues, track already visited pixels, use bounding boxes to limit fill areas, set recursion limits, and optimize the fill direction based on the image structure. To summarize, flood fill is a pixel-based region growing algorithm used to fill connected areas. It comes in two types, 4 connected and 8 connected. It can be implemented recursively or iteratively. It's widely used in graphics and game applications. And with proper optimizations, it becomes highly efficient and reliable. Thank you for watching. I hope this gave you a clear understanding of the flood fill algorithm. If you have any questions or feedback, feel free to drop them in the comments. See you next time.